time, and it took 25 years before we had him back. And but he buses. Once he starts coming, he keeps coming back.
Exactly.
You see, it's on contextuality.
Okay, thank you, Karen, and thanks to the organisers for inviting me. Right. So my talk is about contextuality, which is kind of forced on our attention by quantum mechanics and developments in quantum information. I should say right at the outset that I'm not going to assume any particular knowledge of quantum physics in the talk. And one of the points will be to understand contextuality in some generality. After all, if we want to say that quantum mechanics is contextual, we should understand what it is to be contextual before we come to considering that question, rather than presupposing quantum mechanics. So first of all, I'll say will be based on a recent paper with these people, Rui Barbosa, Kohei Kushida, Ray Light, and Shane Mansfield. The paper was recently presented at CSL conference. But there's also builds on earlier work, particularly Adam Brandenburg and others, and I'll mention some papers at the end. So, what is our topic? Contextuality. Well, it's something that's long been around as what was perceived as one of the really puzzling, quasi-paradoxical, and certainly non-classical features of quantum mechanics. Classic result being the Cauchy-Specker theorem from the 1960s, and you may note that Cauchy and Specker were both logicians. There's recently been a renewed interest for contextuality for its potential as a resource in quantum information processing. For example, a recent paper by Howard et al. In Nature Physics under the title "Contextuality Supplies the Magic in Quantum Computation." A very nice paper by Walter Krausen from a year earlier. So what we're after is some analysis of general concepts. A lot of the literature as developed within physics deals in examples. We'd like to understand things more generally and see what the structure is. And indeed, part of this is to disentangle the general notion of contextuality from the specific case of quantum mechanics. And actually, once we do that, we see that it's a general phenomenon which actually arises pervasively in many fields, and it has some surprisingly familiar incarnations in computer science, for example, as we'll see later. And by the way, non-locality, which is another very important non-classical feature of quantum mechanics, which is the point of the famous Bell's theorem. How many people have heard of Bell's theorem? It's been called, well, anyway, it's in many ways the real starting point for quantum information. Is a special, so non-locality is a special case of contextuality, as it will appear. So we want to say that there's a general structure of mathematical theory of contextuality applicable across these fields. And in a sense, we can speak of a contextual version of probability and so forth. Okay, so I've mentioned contextuality lots of times on this slide. What is contextuality? What's the essence of the phenomenon? So here is what I would like to propose. In a nutshell, contextuality arises when we have a family of data which is locally consistent but globally inconsistent. And once we put it like this, it's not that surprising that it's something that may arise in many situations. So what do I mean by this? Well, just as a sort of image, actually not entirely unrelated by any means to what we'll be talking about more specifically, but let's consider this example just to get a sort of feel for this idea of local consistency and global inconsistency. So we might suppose that we're observing some impressive structure, a tower or something of some kind, and we look at various parts of it, so that we make local observations. Perhaps our camera doesn't take pictures that can encompass the whole structure from where we are, so we look at various corners of it, and we see that each one by itself looks perfectly okay, and not only that, but adjacent pieces fit together in an unproblematic fashion. So we can think of these four pictures we see here as corresponding to four local observations, labelled here A prime, B prime, and they fit together okay in a local fashion. The question is, can we put the whole thing together into a global picture that makes sense? Can we sort of, in some sense, say that everyone, that we can take the whole, we can take a global view of the whole structure simultaneously? Now, if we do that in this case, we get this famous Escher picture of the Escher staircase. And we see that, well, it's problematic if we try and interpret it as a physical structure in real three-dimensional space. It's an interesting point that this figure was suggested to Escher to draw by Roger Penrose and his father. They had a very interesting interaction with Escher. And it's quite related to Penrose's work on visual, on impossible figures. The mathematics also certainly looks similar, although a precise connection hasn't been made yet. Okay, so this is a good picture to keep in mind. Okay, so what do I mean in the title by the borders of paradox? Where are we in relation to paradox? Well, if we now think of these local observations, not just as a sort of arising from some visual illusion here, but they arise with real data that we have to take seriously as giving us as good a picture as we can get of physical reality, then this kind of phenomenon takes us to the borders of paradox. And what I want to say is it takes us to the borders, but it doesn't actually cross those borders. But perhaps being near the border is where interesting things happen, and this seems to be exactly the case in quantum mechanics. So to make a bit of an analogy, it's a bit like the interesting place to be is at the edge of chaos rather than completely chaotic or completely normal. What saves us from a direct conflict between logic and experience, between observable behavior directly giving us paradoxical information, which would be a pretty bad blow if you think about it, is that the data cannot be directly observed globally, which is to say we can't observe all the variables at the same time. So these local pieces of information that we can observe are in themselves consistent. The problem is fitting them all together. And in the sense where this kind of situation arises, it's telling us that it's just in principle can't be possible to observe all the data at the same time. So we could say it's a kind of a priori deduction of the incompatibility of observables, the fact that to observe one thing is to preclude observing at the same time another. Now, of course, in quantum mechanics, if you are familiar with it, you have the phenomenon of non-commuting observables, which gives rise in a specific way to incompatibility. But that's, as it were, the particular realization of this phenomenon in quantum mechanics. But actually we're forced to the conclusion that observables must in general be incompatible in order to preserve ourselves from having this direct conflict between logic and experience. This is what we mean by the borders of paradox. So another general point is that this idea leads to some very interesting and natural mathematical structure. So from this point of view, contextuality is fundamentally about the passage from local to global, these local pieces of information to a global picture that patches all the local pieces together, and indeed more specifically about obstructions to such passages, things that prevent us going in that fashion. And the natural mathematical language for talking about this is sheaf theory. Sheaf theory was developed precisely to talk about the passage from local to global. And in fact, we could even use sheaf cohomology to witness contextuality. And I think this is interesting because cohomology is one of the major tools of modern mathematics, and it's been conspicuously absent by and large from computer science, and with the odd exception. And what is also interesting is that, in a sense, when you're sort of proving some impossibility, some no-go theorem, as it's often famously put, then there's a sort of unsatisfying aspect to this. You sort of posit something as if it could be, and then you show that in fact it can't, and then it kind of disappears in your hands and you're left with nothing, together with the various issues about whether such a proof is, might be constructed from some standpoint or another. The idea with cohomology is that you have an invariant which vanishes when there is no obstruction, but does not vanish, in other words, goes to zero when there's no obstruction, and does not go to zero when there is. So it's something you have in your hand that gives you a witness for the impossibility. And I think that's an interesting perspective on these things. Okay, so enough of generalities. Now let's look at a more concrete situation where we can begin to see what's going on. So here's a scenario which we can understand as computer scientists without invoking any particular physics. So imagine that we have two agents, Alice and Bob, who may, for example, be situated at different places in some network. Alice has a couple of local bit registers, which we call A1 and A2, and Bob has a couple of local bit registers, B1 and B2. What Alice can do, she has a little processing unit, she can choose one of the registers, load it into the processing unit, and observe whether it's 0 or 1. And similarly Bob. When they've done this, they can send the results of their observation to some common place where it can be recorded as a joint outcome. So that's, as it were, a single shot of Alice and Bob going through this process, looking at a register, finding its content, and observing, recording the outcome. We can imagine doing this repeatedly. And as we do this repeatedly, it may not be the case on different occasions that when Alice looks at a particular register, she sees the same value. It may change from one instance to another. And similarly for Bob. So if we do this repeatedly, we get data, we get statistics, and by taking frequencies, we can get probabilities. So here is a model we could make of this kind of experiment that we could do. So it's a model based directly on empirical observation without positing, as at the moment, any theoretical entities to explain it, just what we see. So here's a model, here's a table, which could be a model for such an experiment. So what is this table? Well, you have Alice and Bob with the measurements that they can each perform and the various combinations, the variables they can look at. And you have entries here giving the probability of getting joint outcomes when they look at those variables. So for example, the highlighted entry is saying what? It's saying on those events where Alice looks at A1 and Bob looks at B2, then 1/8 of the time, Alice sees a 0 and Bob sees a 1. Okay? So this is a recording of the observed probabilities of these events. And you see that along each row, for a given choice, conditioned on the choice of which registers are being looked at, you get a probability distribution on the possible outcomes. So you see we have numbers, non-negative numbers summing to 1 along each row. So the natural question is, okay, this is just the empirical data, but is this a possible experience that Alice and Bob could have? Can we postulate a mechanism that would explain this behavior? So here is the most natural way, we might, just using our standard resources, classical computation or classical physics, of explaining this kind of behavior. The thing we could invoke is what we call here a classical source. So there's some process, that's going on, this thing called the source, which at each round is choosing values for each of the 4 registers and writing those values into the registers. And then once it's done that, then indeed when Alice looks at A1, she sees looks at A2 in this case, she sees exactly the value that the source has just written in there. If she looked at the other one, she'd see the value 0, which the source has written in there. And similarly, when Bob looks, in this case, at B1, he sees the value that the source has written in there. And we don't have to assume that the source operates in a deterministic fashion. So it's choosing quadruples of numbers of bit values to put in the registers, because there are 4 registers in this case, And it might be choosing them by sampling from a probability distribution on these assignments. And the question we're asking is, could a classical source of this form explain this experience of Alice and Bob? Could any such source explain this experience of Alice and Bob? So how would we answer this kind of question? Well, let's step back a little and make a brief excursion into some very simple logic and probability theory. So let's make some very simple manipulations that in a Logic 101 course and a Probability 101 course, students could very well be asked to perform. And we'll see that that gives us something that will help us with answering this question. So, we're going to consider the following situation, being a bit more general. Suppose we have some propositional formulas, phi 1 through phi n, and that we can assign a probability to each of these formulas. And the story we're thinking here is the same kind of empirical story we've been telling with our little scenario of Alice and Bob. After all, the formulas are expressions, Boolean expressions in their variables. The variables we can think of as things that can take the value 0 or 1, true or false. And we can imagine performing experiments to test those variables, and each formula describes a combination of possible the satisfying assignments to the formulas that describe some event that we can build out, primitive measurements of these variables. And just by doing a long sequence of trials of measuring the variables, we can imagine that we would get these probabilities, the PIs. But we're making no further assumptions about these probabilities, just that we can assign them to these events. Okay, so that's very anodyne. Now let's make one assumption, one additional assumption, which is of a purely logical nature. Let's assume that the formulas are not simultaneously satisfying, which is to say that any satisfying assignment for n-1 of them, we're just dealing with, by the way, I should say we're just dealing with classical propositional calculus. Now everything is kind of directly measurable quantities. So any satisfying assignment for n-1 of them must make the nth false. Just this is just a rendition of what it means to say that they're not simultaneously satisfiable. And of course, equivalently, this says that if the nth is true, then one of the others must be false. Okay? So, everything is very simple. And now let's make the following deduction under this assumption. So this is what we could do in Probability 101. We use the monotonicity of probability applied to this implication here. The probability of this event must be less than or equal to the probability of this event. We use a very weak property of probability, the subadditivity of probability, to say that the probability of a union is less than or equal to the sum of the probabilities, much weaker than the usual axiom for probability measures. And then just expanding the probability of the complementary event in the usual way, and collecting terms, we get this thing, which gives us the following inequality. Under this assumption that they're not simultaneously satisfiable, the sum of the probabilities must be less than or equal to n-1. An extremely elementary deduction. Is everyone happy with this deduction? I mean, there isn't a catch, but just be aware that we're accepting this deduction unless I hear any argument to the contrary. Okay, so we have, in a very elementary way, derived this bound on the sum of the probabilities. Why is that useful for us? Well, let's come back to our table, and let's now apply what we've learned in this formula to this table. What I'm going to do is, on each row, I'm going to pick out an event, the highlighted cells on the row, and describe it with a formula. So you see on the first row, we have, as it were, the correlated outcomes, either both 0 or both 1. And in terms of the logical variables A1, B1, this is just the formula A1 if and only if B1. Right? The satisfying assignments are just where they get the same values. Similarly, on the second row and the third row, and on the fourth row, I pick out the event corresponding to the anti-correlated outcomes. If one of them is 0, the other one must be 1. And that's just the exclusive OR of the two variables. Okay, so we have 4 formulas. It's easy to see that these 4 formulas are not simultaneously satisfiable. So for example, if we start with A2, I can use this thing here to replace A2 by B1. I can use this thing here to replace B1 by A1. And I can use this to replace A1 by B2. And I end up with B2 exclusive or B2, which is certainly unsatisfying. So therefore, our little trivial deduction must apply. And the probabilities of these 4 formulas must be bounded by 3. All right? 4 formulas, n minus 1. But we can now see that we get a weight of 1 on the first event and a weight of 6/8 on each of the other 3 events. So therefore we get 3 1/4. And we violated our inequality by 1/4. So that's perhaps surprising. Anyone have any comments or want to have another chance to say anything about this? Well, we'll come back to that point, but let's look at another example that shows actually a stronger form of the same phenomenon. And this is a construction due to Lucy and Hardy from the early 1990s. Sometimes it's often called the Hardy paradox, in fact. Again, it's not really a paradox, it's at the borders of paradox in the sense that we were discussing earlier. And the reason that this is stronger is that I don't even need to write the probabilities down. All I need to do is to write down the support of the distributions. So when I write 1 here, I mean it's an event whose probability is strictly positive. So we get 3 zeros, those are, as it were, impossible events, and all the rest are possible. And just from this much information, we can already see that there's a problem of the same kind. Actually, we don't even need to write down all 16 of these values. It will be sufficient to write 4, as we'll see later. But let's anyway proceed in this fashion. So again, I'm going to do the same kind of thing. On each row, I'm going to pick out an event. You see here, treating 0 as true and 1 as false. I'm picking out the event on the first row, which is just A and B. And here I'm picking out the complementary event, which is not A and B prime. That's for the third row, I should say. And for the second row, it's not A prime and B. And for the fourth row, just applying the Morgan duality, it just comes, I'm picking out this event here, which is just A prime or B prime. Okay, so those are my 4 formulas. Again, it is easy to see that these 4 formulas are not simultaneously satisfying. The first and the second gives me what? From the first and the second, I can derive not B prime. From the first and the third, I can derive not A prime. And from not A prime and not B prime, I get a contradiction with A prime or B prime. So they're not simultaneously satisfying. Okay, now what do I know, even without writing the probabilities down, about the probability, for example, of the event on the second row? The event on the second row is the support of the distribution. Sorry? The event on the second...
Is it going to be 1?
Yes, because it's the full support, so the total weight of the probability must be on that event. That's indeed exactly the point. So we see that the probability of the event on the second row must be 1, the probability of the event on the third row must be 1, the probability of the event on the fourth row must be 1. So that's 3. But then I have this event in the top left corner, which has a positive probability. So even without knowing what it is, I know that it has to violate our inequality. The sum of these events, the probabilities of these events, must be strictly greater than 3. So we get a violation of whatever the probability of that event is for the same form of inequality that we were writing previously. Okay, so now let's come back to some reflection on why this is disturbing at a rather fundamental level in terms of our picture of physical reality. In physics, one speaks of observables, quantities you can measure, and after all, physics is all about gathering data about such observables and making predictions, in particular, about future values of observables, or what we will see if we make observations under various conditions. Now, the natural common sense idea on which physics has rested until the last century is that these observables reflect objective properties of a physical system which are independent of our choice of which measurements to perform, in other words, of the measurement context. If you think of Newtonian mechanics, you have position and momentum. It may be very difficult in practice to measure position and momentum, but the whole system of Newtonian mechanics is predicated on the idea that these values have these quantities have well-defined values in any physical state of the system, quite independently of whether we measure them or not. Now, what does this sort of natural, commonsensical point of view mean? It's saying that for each possible state of the system, there's a function which for each possible measurement of some observable quantity specifies an outcome, independently of which other measurements might be being performed. And this point of view, which sort of didn't even need to have a name, as long as it reigned unquestioned as the obvious thing, is non-contextuality. And actually, in our setting, it's equivalent to the assumption of having a classical source to explain what we see. And the point is that this view is impossible to sustain in the light of our actual observations of microphysical reality. So here's more or less the same picture we had earlier, but written in with notations of a more physicsy style. It's actually interesting that this kind of thing was discussed by the physicist David Berman, going in some of his beautiful expositions of ideas and the foundations of physics from the early 90s. And he actually found it natural to use the term instruction set, which is a computer science term, for these assignments of values to all the variables. The only sort of real change in the sort of physics language picture is that we now think of Alice and Bob as performing measurements. And so instead of thinking of these A and A prime and so on as being bit registers, we think of them as measurement settings, different measurement settings. So the point is you have to choose one setting or another, just as before, we have to choose one register or another to load into our processing. So actually the situations are isomorphic. The one that's described in the usual physics scenario and the one we describe in a more computer science kind of work. So coming back to this Hardy construction that we just looked at, often called the Hardy paradox, as I said, we don't even need to write all the values. We just need these four. And it's sufficient to see that there can be no such lambda, and therefore which can account for the possibility of the event in the top left corner, and therefore this non-contextual view is incompatible with a table that looks like this. So even with this much rather little information, it's just incompatible with this non-contextual point of view. And here's the reasoning. For those of you familiar with constraint satisfaction, or it's really a sort of, again, a sort of problem of that kind. What we're asking is, what instruction set lambda could this possibility, could account for this possibility of the event in the top left corner, this 1 over here, which is namely the outcome 0 for A1 and 0 for B1. Well, since this lambda must assign, under the non-contextual regime, a value for every variable, regardless of whether we measure it or not, we've got to be able to extend this assignment to all the variables. And it has to do so in a way that's compatible with the constraints imposed by the table. So let's try and do that. Let's look, for example, at the variable B2. What are the possibilities? Well, there are only two possibilities. Either it assigns 0 to B2 or 1 to B2. But if it assigns 0 to B2, we'd be saying that this event, this joint outcome, was possible, and that's been precluded by this 0 in the table. Therefore, this lambda can't assign 0 to B2, and the only remaining possibility is that it assigns 1 to B2. And now we can do exactly the same thing with A2. We can ask, what can lambda assign to A2? Well, can either assign 0 or 1. It can't assign a 1, or else this event would be possible, and again that's been precluded. So the only remaining possibility is to assign a 1 to a 0 to it. And at this point, we've completely, the constraints have completely forced what lambda assigns to every variable. The problem is, of course, that we still have a constraint left that we haven't accounted for, namely this one here. And according to this assignment, this lambda, this would say that the possibility of the joint outcomes A2 equals 0, B1 equals 0 is possible, and that's been precluded by this 0 here. So the conclusion we come to is that there is just no such lambda, and therefore Hardy models must be contextual. They cannot be explained by a classical source. To see the connection with probability is what we're saying is that the support of that distribution on these global assignments isn't, we're really saying that the lambda will have to be in the support in order to account for the fact that this event in the top left corner gets a non-zero probability. Okay. Well, we might simply conclude from all of this that this was a nice exercise in science fiction, and actually there just is no way that Alice and Bob could have that experience. It just can't happen, because we've ruled out what seems to be the only sort of plausible mechanism we could come up with. However, if we use quantum rather than classical resources, it is realizable, which is why quantum mechanics changes the game as far as information processing tasks are concerned. And more specifically, if we use an entangled qubit as a shared resource between Alice and Bob, then behavior of exactly the kind we have considered can be achieved. And as we've said, this is now, we're thinking of measurement settings rather than which register to load. So just briefly remind you how things look in quantum world. So the quantum analog of the bit is a two-state system so we're dealing with two-dimensional complex vectors, and since they're normalized, we can think of them as, we can represent them on the sphere, on the unit sphere. So they can be arbitrary points on the unit sphere. And spin would be one of the natural quantities that would give us sort of a two-level system. Spin can be measured in any direction. So there's a continuum of possible measurements. There are two possible outcomes of each such measurement, either spin up or spin down in the given direction. And these are represented by a pair of orthogonal vectors. So on the sphere, they just appear as a pair of antipodal points. And this is already a kind of phenomenon of quantization. There are a continuum of possible places the state can be, but for a measurement that we can use to extract information, there are only two possible outcomes here, spin up or spin down in the direction we've chosen. And of course, we should remember that this is a real phenomenon. So going back, I mean, spin in particular goes back to the Stern-Gerlach experiment from the 1920s. This is the block sphere representation of the qubit. Yeah. Well, things get really interesting when, although there are already, as it were, non-classical features in the single qubit, things get really interesting when we have more than one qubit, because then the phenomenon of entanglement arises. So here we have a couple of famous two-qubit systems. The key point is, so if you think of the birth state here, so we can think of it as a superposition of the possibilities of spin-up for both the qubits or spin-down for both the qubits in some fixed, what's usually called the computational basis.